Welcome everyone to my lecture number 18 on fundamental of econometrics for various management sciences. Let me start with week 10. In week 10, this is the second lecture. In the previous lecture, that was the first lecture of week 1, we have covered the consequences of imperfect multicollinearity, and we studied also an example of that. So week 10 is mainly focused on the topic of multicollinearity, and we in the previous lecture look into the what is multicollinearity and how it's affecting if there is imperfect multicollinearity. To give you a quick refresher, multicollinearity refers to the violation of one of the assumption of ordinary least square method that requires that the explanatory variables of a regression model should not be perfectly correlated with one another. If they are correlated with one another, we call it a problem of multicollinearity. Now, there is a difference between multicollinearity and collinearity. When only one correlation exists among explanatory variables, we call it a case of collinearity. If there is more than one correlation among the explanatory variable, we call it a case of multicollinearity. However, for this level, we are considering both collinearity and multicollinearity synonymously. We also discussed in the previous class what happens if there is multicollinearity in our data and we apply the ordinary least square method. So we saw that when there is a perfect multicollinearity and we apply ordinary least square method, the ordinary least square method breaks down. However, if there is non-perfect multicollinearity, then OLS method can be applied, but it has some consequences. The major one was that we get a higher variance or standard error for our beta coefficients. As a result, the t ratios which we calculate become smaller because the t ratios are calculated dividing beta values, estimated coefficients divided by its standard error. So if standard error increases, the t value become lower. When the t value become lower, we end up not rejecting H0, which are supposed to be rejected, and as a result we conclude wrongly that H0 cannot be rejected, whereas it should be rejected. Another consequence is that the R square value being higher, however, the individual coefficients are not statistically significant in our model, or in other words, if there is problem of multicollinearity in our data and we apply OLS method despite having multicollinearity, imperfect multicollinearity, we will be getting a higher R square value, whereas majority or a lot of our variables, explanatory variables, will be statistically not significant. We also saw in the previous class how we can see when we run a model on a data, how we can see for these things, these possibility of multicollinearity in our data using Eviews. We use the data of around 450 working women, and we regress their hours of works on the number of socio-economic variables, and we discuss these consequences of multicollinearity using some real-world data. Today, I'm going to talk about how we can detect multicollinearity, what are the possible remedial measures through which we can fix the multicollinearity problem, and the method of principal component. So let me start. Detection of multicollinearity. So when it comes to how to detect multicollinearity, there is no particular test for multicollinearity, unlike the autocorrelation or heteroscedasticity that do have a proper mechanism or tests for identifying these issues. So to start with, we have no test for multicollinearity. So it's a natural question then, how we can identify multicollinearity? Well, for that we have to stay on some symptoms of multicollinearity. Well, you can when you can look into it, a case of it's a kind of like a disease for which you have no particular test to find what is a problem, but there are some symptoms through which you can find that okay, these are 3-4 symptoms. If this exists, you will believe that this particular disease is there. So for multicollinearity, the same thing exists. We can start with the first major symptom is that you have a high R-square value but few significant T ratios. So focus on this point. When R-square is high, it means that your explanatory variable is explaining the major portion of the variation in your dependent variable. Let's say R-square is 0.98. So it says total variation, if total variation is 100%, 98% of that has been explained by your explanatory variable, but you will also find that not many T ratios or T statistics of your coefficients are not significant, or their probability value will be greater than 0.05 or 0.10. They may not be significant at 5% or 10%. Now R squared 0.98 is very high indeed. For time series it's a normal thing, but for cross-sectional data you may not get 0.98. Something like close to 0.3, 0.4 is considered as a good R-square measure for cross-sectional data. So the first symptom of multicollinearity detection is a high R-square value but fewer significant T ratios. The second symptom of multicollinearity is that there are high pairwise correlation among explanatory variables or regressor. So if you look into the individual explanatory variable and their correlation with other explanatory variable, like comparing two variables and their correlations with one another, you will see that they are very high. And then you have partial correlation coefficient, that's too high. Now don't get confused with the term pairwise and partial correlation coefficient. Now let me show you a bit of the distinction between the two. Pairwise correlation refers to when you look into the correlation between just two variables, x and y variable. You have two variables, you look into it, how they are correlated with one another, you look into their correlation coefficient, that may be any value between -1 and +1. So due to multicollinearity, you will see high pairwise correlation. If you recall, yesterday we did Eviews activity and we also generate one of the correlation matrix of all the explanatory variables. So that was the pairwise correlation matrix, which were looking into the correlation among the explanatory variable with one another and all the diagonal having one value. When we talk about partial correlation coefficient or partial correlation, it refers to a specific case when you have more than two variables. Let's say you have three variables, x, y, and z. So you look into the correlation between x and y keeping z constant. So in that case, in partial correlation coefficient, you have correlation among two variables keeping the third one constant. So that's the difference. So because of multicollinearity, what happens? You have high pairwise correlation among explanatory variable and you have high partial correlation coefficients. So both the pairwise and the partial correlation coefficient among the explanatory variable is being high. And then you have significant F statistic for auxiliary regressions. Now again in your term, F statistic should be familiar to you. F statistic in any regression model shows that how a model fit, or how good is the overall fit of a model. Significant F statistics for auxiliary regression. So what is auxiliary regression? I have a slide on that, so let me go to that slide. Auxiliary regression, in a very simple word, let me start with example. For example, I have a model in which I have one dependent variable yi being regressed on 10 explanatory variables started with x1, x2, x3 till x10. So I have 10 explanatory variable and y is regressed on these 10 explanatory variable. Now for auxiliary regressions, we can think of starting with the first one, in which we take x1. Remember x1, explanatory variable 1, and we regress it on the remaining x variables. So we have a separate regression out of this original model, in which we take the explanatory variable, the first explanatory variable, and we regress it on the remaining explanatory variable. So that's the auxiliary regression. We created that when one explanatory variable such as x1 is regressed on the remaining explanatory variable on the remaining x10 explanatory variable starting with x2 till x10. Similarly, we can generate another auxiliary. This is the model how we can write it, x1 being regressed on all the remaining x10 variable. Similarly, we can do the same for, someone may ask why not x2. So yes, we can do it for x2 as well, and we can regress it on all remaining from x1, and then x2 is all regressed, so skipping x2 and then x4, x5, x10. So x2 regressed on x1, x4, x5 and x10, and we can continue that for doing it for all the explanatory variables. So in principle, when we have 10 explanatory variable, we can generate 10 auxiliary regression estimator. Now there are a number of questions. First, what does this auxiliary regression do? So the auxiliary regression tells us that how one x variable can be explained by the remaining x variable. Now link this with the multicollinearity. Multicollinearity says the relation among the explanatory variables or the x variables. So when you regress one x on the remaining x, it's kind of like explaining one x variable through the remaining x variable. Or in other words, you look into the correlation among the x variables. So that's the intuition behind constructing auxiliary regression model, that you want to explain one explanatory variable with respect to other explanatory variable. So for example, in the first case, when I regress x1 on x2, x3, x4 till x10, this model will tells me that how much of total variation in x is being explained by x2, x3, x4 till x10. So naturally, if this model is a good fit, if its F statistic is high, this means that this x is very much explained by the rest of the x variable, or in other words, this x is very strongly correlated with the rest of x variable. Similarly, we can think of x2 being regressed on the remaining x10 variables, excluding x2 obviously, and we can think of the model in terms of given as follows: x2 being regressed on x1, x3 until x10, and we can again think that how much of total variation in x2 is being explained of all the remaining explanatory variable, and thus we can see if x2 is very strongly correlated with rest of the x variables, and apparently that's what multicollinearity is. So same procedure could be repeated again and again, and we can create 10 auxiliary regression. Now here for the later use, but still we need to keep in mind this one concept which we call principal component or PCs. This auxiliary regression is a a direction toward creating PCs or principal components. We will see that shortly, but for now, we can just say that this auxiliary regression creation is one way of toward moving toward creating principal components or principal component analysis procedure is based on these auxiliary regression estimations. So very quickly telling you or summarizing this thing again, auxiliary regression refers to estimating a regression by taking one explanatory variable out of the number of explanatory variable of your model and regressing that selected explanatory variable on the remaining explanatory variable. And why we do that? Because we want to know that how much of the variation in the dependent variable which we are using in auxiliary variables such as x1 or x2 is being explained by the rest of the explanatory variables. So for that purpose we use this particular model, and through this we want to see if this is a good fit. It is in a way of indication of existing of multicollinearity. So we were discussing that how we can identify the multicollinearity problems. We discussed if there is a high R-square value but few significant G ratios, this is an indication of multicollinearity. Then there may be higher pairwise or higher partial correlation coefficient of the explanatory variables. Again, it's a indication of multicollinearity. Then we saw that auxiliary regressions or the regression generated from regressing one of the explanatory variable on the remaining explanatory variables can generate a high statistic or F test values. So that is also an indication of multicollinearity. Finally, when there is a multicollinearity, you see a high variance inflation factor. Don't be scared. It's a new term. I'm going to explain it in a while. So when there is a multicollinearity, so there will be a high variance inflation factor. Now, look into the construction of this word, high variance inflation factor. So while factor refers to some kind of ratio, inflation, you are familiar with it. So it inflates the value. A true value being inflated. So apparently variance, you know variation as well, and high, you know the meaning of that as well. So high variance, a variance is high because of multicollinearity, and you get an inflation factor or an inflated factor. So apparently VIF or high variance inflation factor refers to a kind of a factor that inflates the variance. For timing, this is the concept. And we have another one which is called tolerance factor. So that's the simple one. You take the inverse of VIF and you get tolerance or tol. So we are going to see first VIF and then we talk about the tolerance factor. So let me go to VIF. So variance inflation factor. Let me explain this with the help of the a model. I will start with a very easy and basic model in which I have just two exponential variable x2 and x3. And we already know that when we estimate these model, and then we can calculate, once we estimate the coefficient beta 1, beta 2, beta 3 using OLS, we can estimate or calculate their variance value as well. So the variance could be calculated by, for example, for beta 2, we have this formula sigma square over summation x2 I square multiply into 1 minus r square to 3, and this formula may sound very complicated. For time being, we will just focus on the first part, ignoring the second part. This formula, you don't need to memorize or look into the derivation of it, but you need to know that when you have the regression being run on Eviews, it do report the standard error and the variances of the coefficient. These are derived through certain formulas, and one of these formula for calculating the variance for beta 2 is given through this particular formula. And now look into this formula. Summation x2 I refers to, now this is small x square and you look into the model, this is the capital one. So the small refers to the deviation from the mean. So small x2 I square refers to the square of the deviation of the mean of x2, or it is x2 minus x2 bar whole square. So that's referring to this value. And 1 minus r square to 3r refers to the correlation coefficient, like the correlation coefficient between x2 and x3, if they are very strongly correlated, will be close to 1. If it's positively correlated, so close to +1, or if it's negatively correlated, it will be close to -1. So what we did is we took that sigma square summation x2 I square separate from this formula, and 1 over 1 minus r square to 3 replace it with VIF. And VIF is named as variance inflation factor, and as I already explained, variance refers to variation and inflation refers to when something gets inflated. Normally we use it for inflation in macroeconomics, is a major macroeconomic variable, but here we are using it in the context of the inflation of the variances because of multicollinearity, and factor because it's a ratio. Similarly, we can think of the variance of beta 3, which can be calculated through this formula. Again, you don't need to memorize the formula, the software does it for you, and we can replace this formula, or we can rewrite this formula while defining VIF as being equal to 1 over 1 minus r square. Now, if you look at these two formulas of variance of beta 2 and beta 3, you can clearly see that VIF is common in both, and you have just the denominator terms different, summation x2 I square. So this VIF is explained on the next slide. Here I will quickly tell you, sigma square refers to the variance of the error term, and x2i refers to the deviation form. For example, x2i is equal to x2 minus x2i. This should be capital X2 minus x2i, and the other term x3i is equal to, this should be again x3 capital minus x3i capital again, and r2 is the correlation coefficient. Now, variance inflation factor. This was the model. So VIF is equal to 1 minus r squared to 3. So it's the variance inflating factor. What does it say? VIF is a measure of degree to which a variance of Euler's estimator is inflated because of collinearity. So in simple word, when we go back one step and we discuss, when we were discussing, I just revised that in the start of my lecture as well, that when there is multicollinearity, the variance of the betas are larger, or in other words, it gets inflated. So VIF is a measure of degree through which these variances get inflated, or VIF tells you the degree of that inflation or increase in the variances. So we say when there is multicollinearity, the variances of the betas get increases, and because of that the t statistics value becomes smaller, and because of that we end up not rejecting H0 when it should be rejected. Now, how much the variances increases? They are increases by VIF factor or variance inflation factor. So now we can look into the relation between VIF and the variance of the estimators in a table. This is a very interesting table. Now, if you look at the first column, that's the value of R23, or the correlation coefficient between the two variables x2 and x3. If there is no correlation, VIF is 1. So put 0 in this equation. So 1 minus 0, that become 1. So 1 over 1 become 1. So VIF values become 1. And you got 0 correlation. So when there is no correlation, or another one, when there is no multicollinearity, VIF is equal to 1, and the variance is equal to k, sigma square or summation x2 I square. So there is no inflation, or there is no inflation increase in the variance when r square is 0.50. What does 0.50 mean? 0.50 mean when x increase by 1%, the x3 will increase by 0.5%, or when x2 increase by 10%, this extreme will increase by 5%. So now look into the VIF value. You can calculate that 1 minus 0.5. This will give you 0.5. So 1 divided by 0.5 and you get this value. Now VIF in that case is 1.33. So when the correlation is 0.5 between two explanatory variables, their variance is inflated by a factor of 1.33. Similarly, when correlation increases to 0.7, VIF is 1.96. So the variance get inflated with 1.96 factor, and so on continuing. The first thing which you should note is that when there is no correlation or when there is no multicollinearity, VIF is 1. However, as you move toward stronger and stronger explanatory variable, the VIF factor increase, and the VIF factor increase is not normal, or the variance increase is not linear. It's very unlinear. Look into it. For the 0, there is nothing, but as you move to 50%, it's 1.33, but then you move to just 20% roughly, and look at here, the jumps are very rapid. So the second concept was the tolerance factor. So inverse of VIF is called tolerance factor, tolerance level, sorry, or it's represented as TOL. That's equal to 1 over VIF. And there is a relation: when R is 1, the TOL is 0, and when R is 0, the TOL is 1. So since TOL is the inverse of VIF, so when a value of VIF is 1, the TOL will be 0, and when it's 0, the TOL will be 1. That's very obvious. So going back to the slide, let me summarize what we have discussed so far. So we started with that there is no particular test of multicollinearity, unlike autocorrelation or heteroscedasticity, which we are going to study in upcoming lectures. In autocorrelation and heteroscedasticity, we have proper statistical tests through which we can check for autocorrelation or heteroscedasticity. However, multicollinearity don't have any test. We have some symptoms through which we try to identify if there is multicollinearity in our data. The first big symptom is that we get, when we have multicollinearity issue in our data and we run regression models through it, we will be getting high R-square value, but there will be very few significant T ratios. Secondly, we get high pairwise and high partial correlation coefficients among the explanatory variables. That's another symptom. High pairwise and high partial correlation coefficient. Then the third one was significant F statistics for auxiliary regression, and I already explained in detail what is auxiliary regression. And finally, we get high variance inflation factor or VIF and high TOL values on inverse of VIF. So this was the theory part. Now in next round, I would strongly advise you, before going to the next content of this video, it's better you take a small break, think about what we have discussed till now, and in particularly focus on VIF. And now in this particular session, starting this session, we are going to see how we can calculate this VIF in Eviews. So again, today we are going to use the same data which we used in our previous lecture. Download this data. If you recall, there were 16 variables in this data. The first one was hours worked by women. So it was in 1975, and then there were 15 other variables like the age of the woman, the education of the woman, her parents' education, her husband education, the hours of works of her husband, the number of the kids under age 6, the number of kids between age 6 and 18, and so on, some other variables as well. So we run this model as well. I hope you remember this model as well, hours being regressed on these all other 15 explanatory variables. And I told you that we are going to discuss that output again, so we will see that shortly again. Now, to calculate VIF in Eviews, the first thing which you should note is that there is no direct way of calculating variance inflation factor in Eviews. There is no a user interface for doing that in Eviews. Our smart author of the book, which we are following as a textbook, have performed these analyses in Stata. I initially thought to do it in Stata as well, but then I realized that it means that I put you for learning in other software. And then interestingly, our author did the principal component analysis. The next topic which we are going to cover in this video was performed in using Minitab in other software. Well, in principle, I can do these all in that software. I have the software and to some extent the command on these softwares. But here, my aim is to put you on learning these things up to certain level which is required at undergrad level, rather than putting you on an exercise of learning so many software and at the end ending up knowing none of it. So I will just focus on what we can do with Eviews, and I will restrict my discussion to that only. So how we can do VIF in Eviews, I will show you through program writing. It's a small 2 or 3 lines writing, and through that we can calculate VIF. So we will do that. For performing VIF in Eviews, the first thing will be that you have to open all the relevant variable in group. For example, in this particular case, we have 16 variables. So we are going to open these 16 variables as a group. Then we have to click on File, top menu. So once you open these as a group, you will go to the File menu, which will be on the top of the window, not the group menu, but the main menu. You go to the File and you open a new program file. So when you go to the file, you get new work file, new program file, and some other options. So you go to the File menu and then you open the program, new program file, and you write a small program. I will show you. It's written here. So if you look into it, well, let me go to the new slide. If you look into it, it says equation EQ1 and then point IS. So equation, I'm defining equation which is called equation 1, and then it is equal to what? Hours being regressed on a constant and the 15 variables. So let's go back. What I'm telling Eviews, that equation 1, this one, equation 1 is equal to this whole model. Hours being regressed on constant. So hours, the first dependent variable, then the constant, then the age, then the education, and similarly experience, family income, and all the remaining variables. So moving forward, the first line of the equation, define equation as equation 1. That's the model which I'm running. The dependent variable hours of work the female were doing, and regressing it on the constant and all other 50 explanatory variables. So that's the first 2 lines. Then the second line, equation 1, then dot, then V, R, I, and F. So I'm asking Eviews that calculate variance inflation factor for equation 1. So I have to write these 2 lines. The second line asks Eviews to generate variance inflation factor from equation 1. So I have to do these 2 lines command in Eviews, and it will generate me the VIF factors in Eviews. So we will do that. I will ask you to pause this video at this stage. Pause this video with this slide being shown on the video. Go download the data of the multicollinearity table, which is on your LMS. Download the data, import it to the Eviews, run the initial model, and once you run the model, then copy this entire equation either from this slide or the slide material I have shared with you, or go to the estimate tab of the result. When you click on that, it will open again the equation. Copy the equation from there and add the first equation. EQ1 point is before the regression, and EQ1 point var INF in the second line while opening a new program file. So do that 2 lines in a new program file. I will show you that on Eviews as well, but first I will ask you to try yourself. Once you do it successfully or you fail to do, then go only for the rest of the video for checking how this can be done in Eviews. So let me switch to Eviews and let me demonstrate how you can do that in Eviews. So once you open the Eviews, I will open the data which we were using yesterday as well. So this is the data I have. Let me run the model first. The model which we have to run was, I am going to regress hours of work the women are doing in 1975, and I'm going to regress it on her age, education, experience, family income, father education, husband age, husband education, husband hours of work, then husband wage, then the kids under 6, the kids between 6 and 18 years, the wage of the woman, then the mother education, then the marginal tax rate of the country where she is working, and the unemployment rate where she is residing. And then I open these as a group first. Now I make this proceed, make equation. Now this is the, I make sure that hours is being regressed on all the remaining variable. I will cut this C. I will take it at the start so that I get beta 1 at the start. I will press OK. So this was the results which I obtained last time. I hope you remember that. Now for VIF, what I asked you, I will go to here to the estimate part. I copy this because then I don't have to type the entire program which is written here. I don't need to type that. So I will press cancel here. I will go here, file, new, and you see there are a number of options. I will go for program. I click here, and if you recall, you can see here as well, there is so look into it. All the variable, variance, inflation factor, then there are coefficient of the variance, and then the variance inflation factor. There are 2 types of variance inflation factor, uncentered and centered. We will just focus on the centered. So once you get this output, compare it with the output you get through Eviews and make sure that it's consistent with what is displayed here. If it's not, make sure you get this output from your Eviews before proceeding further in this video. So now I will switch back to my slide and we'll continue the discussion on this book. So VIF factor output. So this was the output we derived. Now very quickly look into it. What does this output say? First, we have these variables and their VIF. Now if you look at these variables, all the variables have different VIF values. Some have small, some have large. So this is not giving us such a good idea. So I took these values, pasted in Eviews, and I arrange it or sort it in descending order. So this is the table. Now if you look into it, this is kind of MTR comes first because this value was highest, followed by age, which value was 5.7, and so on. Now if you look into it, it gives me some useful information. First, I can see the mean VIF value is 2.83, and then I can see here that some variable have very high VIF values. You can see here ranging from 7 till 1.08, and if you recall, well, first I can see that the first 5 or 4 variable have really high VIF value. By high I mean greater than 2 value. 2.00 or higher is considered as higher VIF. So I will compare it with the table which I show you about the relation between correlation coefficient and VIF. Then give you a better idea about the correlation among explanatory variable. So this is the table. Look into it. F2 explanatory variable correlation coefficient is around 0.80 or well around 0.70. You can see that VIF factor is 1.96, and if you look at here, these 2.02 shows that the correlation here is more than 0.80. So 0.80 is quite high. We last time defined that anything above 0.50 correlation coefficient is high for correlation among the explanatory variable. So 0.80 shows our correspondence to VIF. 0.7 refers somewhere 1.96, which is very, these variables are very much in line with a very high VIF or a possible problem of multicollinearity is with these variables. So this is also one of the potential a symptom of multicollinearity. So that was it. Now the final part of this lecture is to look into the remedial measures of the multicollinearity. Remedial measures, what should be done once we know the multicollinearity? That okay, you may be bored already with a lot of technical stuff, so let me bore you further with adding some more technical things in it. We identified that okay, what is multicollinearity? We know what is multicollinearity. We took the data. We saw that okay, when there is multicollinearity, we know the multicollinearity, and we know what is the consequences, and we know the symptoms, and the symptom says that there is multicollinearity. So what can be done to remove that multicollinearity? Well, in principle, you can't do anything for multicollinearity. Why? Because you have no control on the data. The data has multicollinearity. You haven't generated the data. It comes from other sources. You didn't generated it by yourself with doing some things that ensure that there is no multicollinearity. So in principle, nothing could be done for multicollinearity. So that's the first answer. Secondly, sometime we can redefine our model by excluding some of the variables that are the possible cause of multicollinearity. So, but here we have to be very, very, very careful, because if we remove some relevant variable from our model just because of multicollinearity, we may fall in a problem which we call specification bias. This is also a violation of one of the ordinary least square assumption. So it's a double-edged sword. If you want to drop a variable, you have to be very sure that you are not falling in the trap of misspecification bias. So you can't do anything, or if you want to drop a variable, you have a risk of going for a specification bias. Then there is a third way of solving this multicollinearity problem, and that's called principal component analysis. Now, principal component analysis is a very detailed topic. In this particular lecture, and to your level, I would not go in too much detail of it. I will be showing you some of the basics things of PCA, and for your exam I wouldn't expect more than that what I discuss in this video. So you in principle need to know what is PCA. So that was it. Thank you very much for your patience and bearing me for so long. I hope I make it very clear this topic. In case you have any question, feel free to write me an email, or we will have a group discussion hopefully on Thursday. So we will be then discussing all these confusions you still have. Thank you.